Hello, this is Dr. Hanaa Assil, and these are questions and answers on mass spectrometry. So this is basically for the AS Edexcel chemistry, but it could apply to other courses. So let us take a look at some questions about mass spectrometry. The first question here says, outline how a solid sample of element X is converted into ions in a mass spectrometer. I'm going to remind you that in a mass spectrometer, the first thing that happens is that the sample is vaporized and then it is converted into ions. So we have ionization. That's the first step in the mass spectrometry of a sample. So he is saying, how do we convert the element into ions? Remember that the first thing that happens is the sample is vaporized and then it is bombarded by high energy electrons. So it is subjected to an electron gun. This allows it to be bombarded by high energy electrons. This removes electrons from the atoms to form positive ions. So the positive ions are the ones that will go through the rest of the apparatus. So if we say following the formation of ions, there are 3 steps in the production of a spectrum in the mass spectrometer. So we said first it's vaporized, then bombarded by electrons, so it is ionized, changed into positive ions. And he is saying name the 3 steps that occur after that in order and state how the first 2 are carried out. Okay, so again, in a mass spectrometry, we said the sample is vaporized, then bombarded by electron gun or a beam of high energy electrons, it is ionized. Now, after ionization, the next step is what? The next step is acceleration. And this happens when the positive ions pass through an electric field. So what happens is the positive ions pass through electrodes that create an electric field, and this causes the positive ions to be accelerated. So that's the next step. Now what happens after that? We have passing through a magnetic field, we have deflection. So what happens is the positive ions are deflected by a strong magnetic field, and we said this deflection separates them because the ones with lower molecular mass will be deflected more. So they are separated based on their masses. Then all of this goes to a detector, and we have detection and recording of the spectrum. So these are the steps that happen in the mass spectrometer. The next question says, a sample of neon contains the following isotopes. Remember, we said, what do we use the mass spectrometer for? Well, we can use it to determine the relative atomic mass of an atom based on the relative abundance of the different isotopes. So, for example, here he's talking about neon, and he's telling me that neon has 3 isotopes. One of them has a mass number of 20, and 90.92% of the atoms have this mass. Only 0.26% of neon atoms will have a mass of 21. Only 8.82% of neon atoms will have a mass of 22. So this is what we have from the table, and he's saying what is the relative atomic mass of neon. So how do we calculate relative atomic mass? We said it is the mass number times its abundance, plus the mass number of the other one times its abundance, plus the mass number of the third one times its abundance over 100. If the total abundance is 100, over 100, This gives me the relative atomic mass of the atom. In this case, he wants it to 2 decimal places, so we put it 20.18. Okay? Another example, a sample of potassium has this following composition. So he gives me the different isotopes with their different percent abundance. Again, he's saying calculate the relative atomic mass of this sample, giving your answer to 2 decimal places. Please be careful. Give him what he's asking for. So here he's asking for the relative atomic mass to 2 decimal places. Again, we have the mass number times its abundance, plus mass number times its abundance, plus mass number times abundance over 100. If you get an answer of 39.1344, I do not leave it like that because he wants it only to 2 decimal places. A sample of potassium is known to consist of isotopes with mass numbers 39 and 41. The relative atomic mass of this sample is 39.1. Calculate the percentage abundance of each isotope. So now it is the opposite way around. He gives me the mass numbers and he gives me the total relative atomic mass, and he wants me to determine the percentage abundance of each isotope. How do we do that? You should realize, what did we say? We said if I want to calculate relative atomic mass of a sample, what we do is the mass number times its abundance plus the mass number of the other one times its abundance over 100. And of course, the total abundances of both isotopes would be 100. So if I say that the abundance of the first one is X%, then the abundance of the other one would be 100 minus X, the rest of the 100. So you put this and try to determine what is X. So 39 times its abundance. I don't know what its abundance, so I put it as X. Plus 41 times the rest of the 100. So 100 minus X. And he's telling me that overall, the total is 39.1. So solve for X. So this is a basic math equation to solve for X. So we find that X is 95%. And that means that the abundance of the isotope that has mass number 39 is 95%. Then the other one, of course, would be the rest of the 100. So pay attention to this. This is putting the question the other way around. Instead of giving you the percentage abundance and asking for the relative atomic mass, he's doing the opposite, so you have to know how to do this. Okay, another one. Here he's saying data from the mass spectrum of a sample of pure iron is given in the table. Which species is most likely to cause the peak at m over z 28? So remember that m over z is the molecular mass over the charge. And he's saying that this is iron. And if you look at the periodic table, you will find that the atomic mass of iron is somewhere around 56. So he's saying that we have relative peak height or relative abundance of these, and he's saying one of the peaks gives a mass number m over z is 28. Where did that come from? If my molecular mass of iron is 56, then that means if I have one charge, one positive charge on the atom, then the m over z, remember z is the charge. So if I have one positive charge on the iron, then it is 56 over 1, so that's 56. But what if I have two positive charges on my atom? Of course, he's talking about iron, so C and D are totally wrong. We're choosing iron, we're not choosing silicon or strontium. So C and D are wrong. If I have choice B, the m over z is 56 over 2, and that will give me a peak at 28. So remember that when the atoms are ionized, they have positive charges. Most of them will have one positive charge, but some of them could have two positive charges. In that case, the m over z would be the molecular mass over 2. So in this case, it's 28. How many molecular ion peaks are in the mass spectrum of 1,2-dibromoethane? Assume the only isotopes present are hydrogen with a mass number of 1, carbon mass number 12, bromine mass number 79 or 81. And he's saying I have 1,2-dibromoethane. Remember that the molecular ion peak is the peak for the total molecular mass of the molecule. So what are we doing? We have 1,2-dibromoethane, but then we have two types of bromines. So I could have both bromines 79. Or I could have one of them 79 and the other 81. Or I could have both bromines with a mass number of 81. So in this case, I'm going to have 3 different molecular ion peaks, or 3 different total molecular mass of the atom. Which compound could give a peak at m over e 31? Remember that in the molecular mass spectrum, we have peaks for the total molecular mass and we have peaks for the different fragments. So he's saying which compound could give a peak at m over e 31. That means which of these I can cut it up into a fragment that gives m over e 31. So for A, for example, if I look at that fragment is m over e 31. But the others, if you look at them, you will find that none of them can give a part of the molecule that has m over e 31. Which compound could not give a peak at m over e 43? Again, which of these I cannot cut it up into a part that gives 43? So let's take a look at butane 1-all. Yes, all of this part will give a molecular mass of 43. Butane 2-all, that part gives molecular mass 44. So actually this is the one that cannot give you 43. What about this one? This one will give Mr43. This one will give Mr43. So the one that cannot give you a part with Mr43 is B. Then he says a mass spectrometer operates under a vacuum. Suggest the effect on the ions in a mass spectrometer if particles from the air were present. You have to know that inside the mass spectrum there is a vacuum. So as the positive ions are passing through the mass spectrum, there is only vacuum around them. What if there were air particles around them? Well, that's not good because the air particles would collide with the positive ions passing through and cause them to deflect. We know that the positive ions are supposed to be deflected by the magnetic field so that they're separated according to their molecular mass. But if there are air particles, then these will collide with the positive ions going through and these will deflect the ions from their normal path. Suggest how, if at all, the electric field in the mass spectrometer would affect molecules that are not ionized. Remember that in order to have the electric field affecting the particles passing through, we had to ionize them first. And that is why if they're not ionized, then the electric field will have no effect on the particles passing through. A simplified mass spectrum of an organic compound is shown in this diagram. Which of the following compounds produces the spectrum? Okay, if we have a mass spectrum and I want to know which of these compounds produce this mass spectrum, the first thing I do is I look at the m/e of each peak. So what are the peaks that we have? First, you look at the peak with the highest m/e. So here we have the highest m/e is the peak at 58. This is the highest. We call it the parent ion peak or the molecular ion peak. And that is the peak showing the molecular mass of the molecule. So if I want to know this applies to which molecule, it has to apply to a molecule that has a total molecular mass of 58. Then there is the base peak. We said the base peak is the one with the highest percent intensity. So here we have a base peak at 43. That tells you that if you cut the molecule into fragments, there should be a fragment that has a mass of 43. And there is another fragment that has a molecular mass of 15. So which of these agrees with this analysis of the mass spectrum? So if we look at propane, this is propane. What is the molecular mass of propane? If you calculate the molecular mass, it's 44. So this is not my answer. I am looking for something that has a total molecular mass of 58. What about propane 1-all? If we sit down and do the molecular mass is 60. So that's not my answer either. Propane 2-all, also molecular mass 60. But let us look at propanone. We said propanone is a ketone, and if we look at the total molecular mass of this molecule, it is 58. So that is correct. And I have a fragment, a part of the molecule that has a molecular mass 43, and that other part with the carbon with 3 hydrogens, that is molecular mass 15. So this is actually my answer. That is the mass spectrum of this molecule. The reaction of ethene with aqueous potassium manganate produces ethane 1,2-diol with a molecular mass of 62. Now remember that potassium manganate is an oxidizing agent. When it reacts with ethene, the alkene is oxidized to give a diol. So we put OH on each carbon that had the double bond. So he's saying in an experiment, potassium permanganate containing only O18, so the oxygen from the manganate is O18, reacts with ethene. So just how the mass spectrum of the product, ethane 1,2-diol, could be used to decide whether the oxygen atoms in this product came from the manganate ion or from the water or from a combination of the two. Remember, he said the potassium manganate, the oxygen in it is O18. The water would be O16. So how can I use the mass spectrum to determine these two oxygens that are in ethane 1,2-diol? Are they from potassium manganate or from water or from both? Well, that's easy. Remember that we said looking at the mass spectrum, we're basically looking at the parent ion peak. Remember, we said the parent ion peak is the peak with the highest molecular mass. So if both oxygens are O18, then calculate the molecular mass of ethane 1,2-diol in which the oxygens have a mass of 18. This will give a parent ion peak at 66. Now, if one of the oxygens is O18 from manganate and the other oxygen is from water, which is O16, then calculate the molecular mass of ethane 1,2-diol with one of the oxygens 18 and the other 16, then I should have a parent ion peak at 64. If both oxygens came from water, then the oxygens in the ethane 1,2-diol are 16, then there will be a parent ion peak at 62. A student sketched the mass spectrum of chlorine gas, which contained 75% of chlorine 35 and 25% of chlorine 37. So the student wrote this mass spectrum or sketched this mass spectrum, but this is wrong. And he's saying identify and correct the two errors made by the student in this sketch. So what is wrong about this spectrum? First of all, we're saying that the chlorine, we have two isotopes of chlorine. Chlorine 35, 75% relative intensity, and the chlorine 37 should be 25% relative intensity. So that means that the peak for chlorine 35 should actually be 3 times the height of the peak at 37. So the heights of the peaks are not correct. He wrote them equal. They're not equal. They're not 50% for each isotope. The peak at 35 is 75% and the other one is 25%. So the peak at 35 should be 3 times the height of the peak at 37. Now, what is the other mistake that he did? Remember that we're saying we have 2 isotopes of chlorine. That means the chlorine molecule that has 2 chlorines, both of them could either be 35 or both of them 37, or one of them 35 and the other 37. So I should have in there, he already put a molecular, a peak for molecular mass of 70. So that is correct. And he put one at 74, but he did not put a peak for 72, where one of the chlorines is 35 and the other is 37. So there should be a peak at 72. Give the formula of the ion responsible for the peak at 74. So we said this is the peak at 74, and we said the 3 choices that we have are either both of them 35 or both of them 37 or one of them 35 and the other 37. So the peak at 74 is the one for what? Is the one in which both chlorines are from the isotopes that have a mass of 37. This is how you write the formula of the ion. So the ion has to be a positive charge, and we want the one in which the first chlorine has a mass of 37 and the other chlorine has a mass of 37. The mass spectrum of propane 1-ol is shown. Which peak represents the molecular ion for propane 1-ol containing a carbon-13 isotope? Remember that this is propane 1-ol. Now, if I sit down and calculate the molecular mass of each one, the molecular mass in the periodic table is 12. But carbon has another isotope with a mass of 13. So if I have a carbon-13 isotope in one of these carbons, then my molecular mass would be 61. So that is the peak that he labeled D. Bromine has 2 isotopes, 79 and 81. The presence and abundance of these isotopes can be determined by using a mass spectrometer such as that shown in the diagram. So this is a diagram that he gives me for the mass spectrum. Explain how ions are produced in the area labeled A. We said the first thing is we pass in a sample that is vaporized, and then what happens at A? We said at A, the sample is bombarded with high energy electrons using an electric gun. Electrons are lost from the sample, forming positive ions. So positive ions go through the rest of the apparatus. State what is used to deflect the ions moving through the mass spectrometer. So this was the diagram. We said we're going to pass it through electron gun and ionize it, and then it will pass through an electric field. Remember what happens in the electric field? the positive ions are accelerated, and then it passes through B. What is B? B is the magnet that helps to deflect the ions, and we said it deflects them based on the differences in masses, so that the one with lower mass is deflected more than one that has a higher mass. Explain why there is a vacuum in a mass spectrometer. Again, remember we said we need a vacuum inside the mass spectrometer, because if we had air, the air particles would collide with the ions and interfere with its movement. Complete the mass spectrum below for a sample of bromine gas. Bromine gas means I have bromine molecules, Br2, that contains approximately half of them Br79 and the other half Br81. Okay, remember bromine gas means I have bromine molecules, and I have, when we bombard them, we break them up, and one of them, the fragments would be the individual atoms. So these are the different choices that we have. I have a peak for the Br79 and a peak for the Br81, and he says they are approximately half and half. So they are the same relative intensity. Now, when we have a combination of two bromine atoms in a molecule, then both of them are either 79 or both of them are 81, or one of them is 79 and 81. And remember that the intensity for the 79 and 81 is twice the other ones, because I have two choices. Either the first bromine is 79 and the second is 81, or the first is 81 and the second is 79. So remember that the peak for Br7981 is twice the peak for both of them 79 or both of them 81. Calculate the relative atomic mass of bromine for a sample which was found to contain 47% of bromine 79 and 53% of bromine 81. And he says give your answer to three significant figures. So again, what we're doing is just the abundance times the mass plus abundance times the mass over 100. Remember that he's saying give your answer to three significant figures. So is 80.06 my answer? I have to put it in three significant figures. What would be the effect, if any, on the m over e value of the peak if the ion detected has lost 2 electrons rather than 1? Remember that the peak is m over e. E is the charge. So if the mass is 80, then if it has a charge of +2, then the m over e value will be half the original value. So instead of having m over e at 80, it will be m over e at 40, because it is the molecular mass over 2. One of the uses of mass spectrometers is for detection of banned substances, such as anabolic steroids, in a blood or urine sample taken from competitors in sports events. So just two precautions that are necessary to ensure that the result of any analysis would be valid. Okay, so we said one of the uses of mass spectrometry is to detect the presence of anabolic steroids in blood or urine for sports competitors. So what precautions should we take to make sure that the analysis is correct? Well, any two of these could be correct. So we could say the temperature of the sample should be controlled. We should repeat the analysis more than once to confirm the results. Take the sample immediately after the event and ensure that the sample is obtained from the named athlete. Any suggestions like this would be correct. These substances can give competitors an unfair advantage. So competitors that use anabolic steroids have an unfair advantage. So just why the use of these substances may be of concern to the user. Actually, it is harmful to use these anabolic steroids because they may cause harmful side effects such as liver damage or heart attack, or if they're taken by female competitors, it gives them masculine features in the female competitors. Ions are separated in the mass spectrometer by, again, where do we have ions separated in the mass spectrometer? This is in the magnetic field, where we have deflection of the different particles with different masses. The correct sequence for the processes that occur in a mass spectrometer is what? Again, what are the correct sequence of processes? We said first it's vaporized, so vaporization, and then ionization, and then acceleration, deflection, detection. So A is my correct choice. Which of the following ions would be deflected most? Remember, we said when it goes through the magnetic field, it is deflected. And we said the ones with the lowest molecular mass are deflected most. The ones with higher molecular mass would be deflected to a lesser extent. So which of these will be deflected most? It's the one that has the lowest m over e. So looking at this, of course, A has m over e 35, B has m over e 37, but C has m over e 37 over 2. Of course, D would have 35 plus 37, so that is big also. So the one with the smallest m over e is the choice in C. Isotopes can be separated in a mass spectrometer. In the diagram below, particles are ionized at A and detected at D. Now name the processes occurring in the mass spectrometer at B and at C. We said what happens at B? We said this is the particles are going through an electric field, so this causes acceleration. What process happens at C? We said they're going through a magnetic field, so the process that happens to them is... Okay, here he's saying the mass spectrum of an element is shown. So he gives me the mass spectrum and he's saying the relative atomic mass of this element is what? So you get from the mass spectrum the mass of the isotope times its abundance. So obviously we have an isotope at 69 and its abundance is about 60. Plus, there is another isotope with a mass of 71, and its abundance is about 40, and you calculate that, so that comes out to be 69.8. In a mass spectrometer, positive ions are accelerated by what? Remember, we said they are accelerated by passing them between charged plates. Explain how it is possible to distinguish between individual chemicals using their mass spectra. We said we can use mass spectrum to distinguish between different chemicals because different molecules will give different peaks due to different fragmentation. So when we look at the mass spectrum, we look at the parent ion peak to show the molecular mass, and we look at the peaks due to the different fragmentation, and they should agree with the molecule we are identifying. Bromine has two isotopes with relative atomic masses 79 and 81. Which of the following values for mass over charge ratio could correspond to a peak in the mass spectrum of Br2? You should assume that the ions detected have a single positive charge. So we're saying we have Br2. Now, which peaks do we have? We said, in this case, either both of them are 79, then I should have a peak at 158. Or both of them have a mass of 81, so I should have a peak at 162. Or one of them is 79 and the other is 81, so I should have a peak at 160. So the one that could be found for the mass spectrum of Br2 is a peak for 160. Okay, another question says the molecular ion peak or the parent ion in the mass spectrum of a hydrocarbon containing carbon-12 and hydrogen only is which one? What do we mean by molecular ion peak or parent ion peak? So if we look at the mass spectrum of any hydrocarbon, for example, pentane, what is the parent ion peak? It is the peak with the highest mass to charge ratio. That is the peak that shows the molecular mass of the whole molecule. And then you have other peaks showing the masses of the different fragments. But the parent ion or the molecular ion peak is the one with the highest mass over charge, or M over E. In a mass spectrometer being used to determine relative atomic masses, gaseous atoms are ionized. So again, let's remind ourselves. Explain how atoms are ionized in a mass spectrometer. Do you remember that? How are atoms ionized in the mass spectrometer? We said the sample is bombarded with high energy electrons from an electron gun. How are the ions accelerated? We said we pass them through an electric field. How are the ions deflected? They are passed through a magnetic. Okay, and that's the end of this lesson. I hope this was useful to you. Thank you for listening, and please continue listening to the videos. Thank you.